So in this video we're going to be talking about the approximation of square root 2 with the utilization of this infinite continued fraction. So actually you are seeing an infinite continued fraction here which approximates square root of 2 pretty rapidly. So this fraction 1 plus 1 divided by 2 plus 1 divided by 2 plus so on and so forth gives a very rapid and accurate approximation of square root 2. And now I want to look at the intuitive idea of why this approximation works in the first place. So the fundamental consideration is that you are splitting up this expression square root of 2 equals to 1 plus square root of 2 minus 1. And now you want to manipulate the second expression. Actually, you can write it as a fraction, square root of 2 minus 1 divided by 1. So the denominator is 1. And you want to make it more resemble to the desired expression. So you want to get rid of the square root expression in the numerator. And what you end up doing is that you are multiplying both the numerator and the denominator by square root of 2 plus 1. And after expanding this expression, what you end up obtaining is the square root of 2 equals 1 plus 1 divided by 1 plus square root of 2. And actually, you should obviously see it that in the denominator, the expression, the entire expression, just appears. So what you want to do now is to achieve this desired form, is to substitute square root of 2 with the entire expression. So when there is square root of 2 in this expression, you are simply substituting it by 1 plus 1 divided by 1 plus square root of 2. So you end up obtaining this particular form. And after simplification, you just observe that 1 plus 1 equals 2. So you obtain this square root of 2 equals 1 plus 1 divided by 2 plus 1 divided by 1 plus square root of 2. And you can actually do this iteration forever and thereby get an intuitive idea of why this original expression works. So now let's just look into how rapidly this fraction approximates square root of 2. So a1 is the first iteration, it's obviously 1. Now the second iteration is 1.5. Now you should consider that it's already pretty close to square root of 2. And when you're doing the third iteration, it's already 1.4. It's not that far away from square root of 2. And actually a4 is 1.41666. And I have calculated some of the approximate values of the squares of these iterations, and you can actually observe that the fifth iteration, the square of the fifth iteration is 2.0002, which is enormously close to 2. And thereby you can have an empirical sense of how well the square root of 2 is approximated by this continued infinite fraction. So actually what we were doing is that we solved this equation, this quadratic equation, in an iterative manner. So the iteration stands as follows. So the first element of the sequence is 1, and now you can calculate every element, every consecutive element of this sequence by utilizing this formula. So you add 1 to the 1 divided by 1 plus the previous element of the sequence, and this iterative formula gives you a convergent sequence by which the solution of this quadratic equation can be obtained. Now, there is a conspicuous advantage of this representation. Actually, if you're observing the decimal form of square root of 2, you can see that there is not much a tremendous pattern, which is kind of striking. So it ends up being pretty chaotic. But if you are looking at the coefficients, the members of this sequence which are appearing in this infinite continuous fraction, 1, 2, 2, 2, 2, 2, you end up observing a pattern in which previously you have not observed a pattern. And we have already seen the infinite continuous fraction form of 1 plus square root of 5 divided by 2, and the decimal representation, this 1.61833, etc., is pretty chaotic. It's not really showing us a pattern, a well observable pattern. But if you are dealing with the infinite continuous fraction representation, what you are getting is 1, 1, 1, 1. So the pattern is way more obvious. So it gives us order when there wasn't really an order appearing. And actually, this idea of solving quadratic equations with iterations can be done in this specific form as well. So lambda squared minus a lambda minus 1 equals 0. What you are doing is you are rearranging this equation, and you are dividing by lambda. Lambda is greater than 0, and a is greater than 0 as well. So you are obtaining this specific equation, lambda equals 2a plus 1 divided by lambda. And you can actually write an iteration to this one as well, just like in the case of the square root of 2. So you observe that this lambda is the same as the entire expression, so you end up substituting a plus 1 divided by lambda in the place of lambda, and thereby obtaining this infinite continuous fraction. And in the left side of this equation is obviously the positive root of this quadratic equation given by the formula. Now you can kind of very easily associate the sequence a with this particular expression, a plus square root of a squared plus 4 divided by 2. So in the vast majority of the cases, you wouldn't really find pattern in that left expression. But after you are considering this infinite continuous fraction representation, you end up obtaining a pattern. Thank you so much for watching.